All right, so we're going to start moving into volume. We're going to start with what's called volumes using known cross sections. This is one of calculus's biggest claims to fame. It's where all volume comes from and all geometry formulas come from. And so we're going to use the use the idea of slicing. So kind of think of slices. The only thing right now, well, there's a few things you should know how to find the volume of, right? In elementary school, what's the first shape they teach you to find the volume of? Geometric, but which one in particular? Like right after you learn about rectangles and area. And then going, now to get the volume, you do length times width times height. And that's the volume of a what? Volume of a what? Thank you. A box, basically, right? Length times width times height. Now, here's the deal. The reason it's length times width times height is because when you have the box, length times width covers or gives you the area of the bottom. The height gives you depth. Okay? Same with the cylinder. It's pi r squared h. It's covering the bottom and then giving it its depth, right? That actually is the theory behind the formula for the volume of anything. Is you find the area of a face. So I'm going to show you that. I'm going to go down here with this sketch, and I'm going to try my best to draw a loaf of bread. I'm not a very good drawer, so let me try. You can try too. Let's make that's a slice of bread right there. Who would have thought in math class you're going to be drawing bread, right? That maybe, like that. I don't know. How am I doing? Not very good, Clocker. Does that look like a loaf of bread?
Not really.
Oh, I wanted it to. Oh, well, here, I'll give this slice some depth. Maybe that'll help. A slice of bread. Here's a slice. Did that help, Priestley?
A little bit.
A little bit. Well,
it's a good loaf of bread.
Yeah, I don't know. I'm not. That's why I have a whole bunch of visuals for you today. Drawing is not my strength, and so I'm going to let the computer and I let the BC kids do it. But it's kind of good enough. The idea of slices is if I were to bring that loaf of bread in here, and I were to start cutting it and handing you each a slice until it was gone, if I pulled together all your slices, wouldn't I get the volume of the loaf? Right? But the theory of integration is that I slice that so paper thin that I can give an infinite number of people an infinitely thin slice. Does that make sense? I blew up a bigger slice. The volume of your slice, though, Ellie, is found by taking the area of the face. If it was purely square, like those, have you ever seen those mini rye bread, those where they're little squares, right? If it's completely square, I would just do length times width, and I'd get the area of the face. This is the depth of your slice, which approaches 0 as I make an infinite number of slices. There's your 3 dimensions. Area is 2 dimensions, and the dx, or the thickness, because again, I'm going to be putting this on the coordinate plane. There's my bread sitting in the first quadrant. That's pretty bad. I'm sorry. Right? And if I were to integrate across the loaf, basically cut an infinite number of slices and integrate each slice. This means add them all up, right? From A to B. This means so thin you can't see them. That's their depth, and then the area of a face. That's what that formula means. Does that make sense? Sort of? So today what we're going to do is not bread. They're all going to be geometric slices. So I'm going to have you tilt your y-axis and sort of tilt your x-axis. And you're going to picture it laying on the ground. All right? So picture that 2-dimensional shape on the ground coming up out of the paper or off the ground. Actually, we call this a z-axis, but you just have to picture the fact that X and Y are 2 dimensions. It's on the ground. So here's a sample that one of the BC kids made yesterday. They've got their X and their Y on the paper, but you see how these are coming up out of the paper, right? Semicircles, correct? Your goal is going to be to find the volume as if there were an infinite number, and it's kind of like the metrodome. All right? So what you do here, set that right over there, is you're going to have a base. I call it the bread loaf pan. All right? On this one, you can see they all use Play-Doh as their base. They actually did that root x and x squared intersection that was on your number 5. That's what they graphed on here. This was root x. This was x squared. They intersected 0 and 1. They covered the bottom of the pan with Play-Doh, right? Stuck it in the oven, and this person made a loaf for making Triscuits, right? They're triangular, aren't they? No. What's the cracker that's triangular? Doritos. Right? Dorito bread. All right, so what we do is we take that base, we put it in the oven, and they'll tell you what you're cooking. We're going to cook it up so that when I slice it, you each get a square, let's say. So you have to picture this coming up out of the paper, making a square. And how many of them are there? What do you think, Claudia? How many squares are there as I go all the way across here? Infinite number. They're all, like, you want one in the middle if you like it. If it's like communion bread and you're like, ooh, I don't like it, then you want one at the end. They're different shapes, right? They're functions. The question becomes, how do I find the volume of that shape? You're still going to say, I need to do the area of a face. But if it's a square, what's true about this side and this side? Go ahead and tell me. Same. Okay? We already know how to get this length. How do we get that length from we just did it, right? How do we get it? Go ahead and tell me, Lily. How do I get that length that I just bracketed off? Let's put function names on here. Maybe this top one is f of x, and this bottom one is g of x. How do I get this length? What do you think? F of x minus g of x, top minus bottom. Okay? What we're now going to call that is s of x. It's going to stand for a side of our figure. We're always going to drop it perpendicular, almost always to the x-axis. It's called s of x. Well, Kaden, if that's s of x, guess what this is? S of x. It's a square, right? Who did the squares? It's this one. So you can see, here, look, you can actually see it. If I pull this one out, they've got that bottom stretching across from the top to the bottom function. Can you see it? That's also how high it is. So we do s of x, top minus bottom, times s of x, right? That'll give me the area of this, one of them. But I need to give it its depth. Does that make sense? So for the square, it's going to be a side of it squared, dx. And again, how'd you get a side of it, Lily? Top minus bottom. Now I'm going to show you some better visuals, because my bread, it's hard to do 3D on a two-dimensional sheet. So just give me 1 second. I'm going to hop on GeoGebra here so you can actually see it. And that's why your assignment is going to be Delta. Excuse me, because they sketch it for you. So I'm going to hop on here. Just give me a second to delete this. Delete this. I'm going to just get all this crap out of the way. I think I'm going to refresh. And I'm going to show you these a little bit better. I think I have to re-enter it. It didn't like me. All right, there I can see it. All right, so GeoGebra has put, and let me go full screen on you so you guys can see it a little better. All right, and let me know in the back if you can't see it very well. All right, how are we doing in the back of the room? Can you see, Sam? So I'm going to pick squares first of all, because that's the one I just started with. So I'm going to click on squares, and it pops one up out of the paper off the floor. My bread loaf pan is the intersection of the red and the blue. My square side stretches across the top. That's why we do top minus bottom. And again, if you get the visuals of these down, it's going to be super easy. All right, so I have that stretching across. I'm going to make more of them and more of them. And as I stretch them across, you'll notice I'm getting a solid. It's got a curved top, even though I'm making it with squares. Does that make sense? Maybe this is some amphitheater somewhere. Can you visualize it? Its volume will be each one of those squares I need to add up. So when I do the one square, let's go back here, I need to find its volume. Now watch the equilateral triangles. Let's pop those up on there. Okay, so let's pop up some equilateral triangles for a while. I'm going to stop. Here's its cross section. Right here, it's like a Dorito. But again, do you see how the side of the equilateral triangle is still top minus bottom? You're going to be doing top minus bottom for all the sides. Semicircles popping out. You can still see that the diameter of the semicircle is still top minus bottom. And the depth of everything is always a little change in the x-axis. So we always have that third dimension being dx. So any questions about that, Priestley? Kind of what they look like? Because I can't draw them very well. All right, so usually we do really well on these. I compensate for my weakness by finding people who can draw well. And maybe the BC kids made those for me yesterday. I'm like, guys, you know I can't draw. And so they came in and helped and made some of those for me. So what we're going to do is go back to our notes, and we're going to get the theory of it down on the bottom, and then we're just going to go practice. All right? So down on the bottom, here's what you're going to be doing. If we can find the area of a face, what do I mean by a face? The face of it. Right? Area of a square, area of a triangle, area of a semicircle. They'll be geometric for the most part today. We're going to run perpendicular to the x-axis 90% of the time, which means dx problems. But sometimes they'll say perpendicular to the y-axis, and you might ask yourself, how do I know which is which? Like Luke said, if it's perpendicular to the y-axis, your functions will be given as functions of y, not x. So you'll spot them just like you did on your assignment. We can find the volume of the whole solid by integrating across the integral. The dx or the dy gives us the depth. Length times width times height, pi r squared. H from geometry, they all have a depth in their formulas, right? So the dx or dy gives us the depth, or what we call the third dimension. The area of a face gives us 2 dimensions. Dx gives us the third. So on this next page, we're going to have a whole bunch of formulas. Do you need to memorize them? Sort of. But you should be able to visualize and know most of them. So we're going to call this distance right here across the base our s. And almost always it'll be a function of x. So I'm going to call it s of x. Top function minus bottom function. This is actually the Plato one. The top function was y equals the square root of x. The bottom function in blue was y equals x squared. That's actually what these guys use, like this. Okay, so that one you're looking at is this guy. I know he's falling down, but so can we visualize? Are we good? That's this one. All right. To get that s of x, we're going to do what Lily says. We do top minus bottom. Unless, Lily, it's a dy problem, which it will be maybe 1 out of 10 times. How is that going to change? Instead of writing top minus bottom, what would I have written? Right minus left. Yeah. All right. So for squares, for all of them, I'm going to do the area of a face dx from left to right. It's just this that's going to be changing. All right, are you ready? So for the squares, I'm going to integrate across the base, area of a face, area of a square, side times side, so s squared, and then what will give it its depth? Go ahead. This is 2 dimensions right now. It's s times s. What gives it It's depth. dx. Excellent. So I put the dx on there. That's your formula. And again, this is just top minus bottom. You shouldn't need to memorize that, Bryce, because you should know that from geometry, right? Now, the isosceles triangle. Do you guys know what an isosceles triangle has? When it says isosceles, what do you know about it? You know, Sam? Two sides are the same. Yeah, and if it's an isosceles, it's actually going to be an isosceles right triangle. Really what it'll be, that's why I didn't draw a sketch over here. An isosceles right triangle is really just a square that's been cut in half. Right? So guess what the formula is? Exactly the same as the square. But guess what's out front of it? A half. That shouldn't need to be memorized, right? So we try to visualize before we're going to go to do, but I still need to do side squared, A to B, but this isosceles triangle right here is 1/2. Where is 1? Here we go. This guy right here is the isosceles right triangles with the leg across the base, half of all the squares, right? This was Katie, and she got an answer of 0.064. The square one, 0.128. Because that's half of this. Does that make sense? All right, so if you can do one of them, you can do all of them. The next one down here, rectangles. Well, again, let's pick on, how about Shump? How do you get the area of a rectangle?
Base times height.
Yes. Base times height, length times width. Agreed? We still have this s that stretches across the two functions. So that's going to give us the base. The height of the rectangle is not s. Okay? You will have to be told it. You might say the height is 4. You might say the height is twice the base length, and you do 2s of x. But you have to find or be given that height. Because you just said base times height, correct? What's my third dimension? Because right now you found the area of the base of the rectangle. What's the third dimension, Harrison? dx. All right, so I'm going to point at that h. You might say, what is it? It depends. If Charlie, they say the height is 3, then that's a 3. For this one that's flopping over, it was my fault because I told Maya to do a rectangle whose height is twice the length of the base. And little did I know it was not going to be able to support itself, right? But when its height was twice the length of the base, then I had to do that. If it was constantly 3, you'd see them sailing along all the same height. But this was a function of, do you see the difference? All right, really need to visualize today. I'm going to wait on that hypotenuse. All right, semicircles. Kaden, how do you get the area of a circle?
Pi r squared.
Okay. How do you get the area of a semicircle?
Half pi r squared.
Okay. Down here, whoops, I'm going to need a different color. Down there on the bottom, let's go right here in black. That's not the radius. That side length for the s of x is the diameter. We're nodding? All right. So this right here, top minus bottom, s of x is equal to the diameter. So before I plug it in, Kaden, you're deriving the formula right now for me. What do I need to do with that diameter before I plug it in for the radius? Half it. Okay. So here's what we have. 1/2 pi radius squared. But this distance between the two functions that Lily said is top minus bottom, and I said we're going to call it s of x this whole section, right? That's the diameter, so we have to cut it in half. Watch me clean this up. I'll have a pi. I'll have a half. And then do you see how I'm going to have a fourth as well? Right, Kaden? Because I would have this square down here. So there's actually a pi eighths, what I call multiplier. You do need to memorize that. But if I can show you it being derived and you just did it, you'll probably never forget it because you're the one who talked me through it. So we have to do pi a's times the integral from a to b, side squared dx. In Harper, how did I say we get that side? Well, in general, it is the diameter, but how would I find it? How do I get that length? Always. Go ahead, Lily. Oh, got it? Top minus bottom. Yeah, all right. Equilateral triangles, rarely will you see, because kids forget the multiplier up front. So I'm not going to derive it. I'm just going to tell you it still has the s squared in it and the dx, but there's a root 3/4 in front of it. Somebody in BC who made the equilateral triangle one for me yesterday, where did that one go? I don't know where I put it. Oh, it's on the chair. Said I can't remember if I put a root 3/4 or a root 4/3 in front of here. And I said, think about it. And then, oh, why? How'd they just settle on root 3/4 instead of root 4/3? Right, Felicia? What's root 4? 2. Then I just need 2/3, right? So you're going to need to memorize that one. Luckily, it rarely shows up on the AP exam. Same with this one. When we put the hypotenuse across the base, I'm going to draw, by the way, a square. That one's side squared. When we put a leg across the base, we have 1/2 side squared. When we put the hypotenuse across the base, it would be like one of these, like leg hypotenuse. Do you see how that's kind of a fourth? There's a fourth multiplier in front. Now we're going to go practice. It's actually really easy if you can visualize. Are you ready? Ready, 40? Next page. Here we go. First thing you need to do is get a sketch. Sketch, sketch. The volume of a solid is base, that's the bread loaf pan, x plus 1. So there's a line going like this. That's going to make the shape of my bread loaf pan. X squared minus 1. What does that make, Frank? X squared minus 1? What is that? Parabola. It opens up from 0, -1. That's really all you need to do is know how to sketch it. Okay? And it'll be pretty easy, just like I think we forgot e to the x. Oh, shoot. So I'm going to go grab my highlighter. I'm going to shade in that bread loaf pan real quick here. You're picturing this being flat and laying on the ground, and you're going to build up off of it. The formula for all of these is area of a face dx. My limits for all of them are the same. How do I find the limits? How about today? Ava, how would I find the limits?
You would do top minus bottom.
That's S. Okay, so let's write that down. S of x equals top minus bottom. The line's on the top. So let's do that. X plus 1 minus x squared minus 1. We need that for all of these. We need to figure out, well, what is this? Because it's a side of every single figure. All right, so let's clean that up. It'd be a negative x squared plus x plus 2. All right, that'll help. How do I get the limits?
Isn't it just the x values of it?
X values of the intersection points. This is a dx problem. How do I know that, Luke? That it's a dx problem?
It's y equals.
It's y equals. It's all about x. Okay? You are correct. Annika, how do I get those intersections?
You set the equations equal to each other.
Yep, go do that. Set the equations equal and get me those limits. I'll take a blur. Did you have them, Charlie? Clocker, what were they? 2 and -1. Do I have a backer? Yep, we're nodding. Awesome. Thanks, Sam. So for all of these, we're going to be integrating from -1 to 2. Now you just have to remember, without looking, now it's going to be hard because this is our first one, but once you do a few. For squares, how do I get the area of a square? Side times side. What's the side? Top minus bottom, which I already did. There's one side, 2 sides, side times side, depth from -1 to 2. That would probably be calculator active because that'd be ugly to square that one. So we're going to move on. Rectangles with a height of 2. I want you to set it up. Rectangles with a height of 2. You needed 3 dimensions for the rectangle. Height is constantly 2. It's one of the dimensions. You nodding? It's not really memorization, is it? So let's go take a look. Height is constantly 2 for those rectangles, so it doesn't matter, they're all the same height. So 2 is one of the dimensions. What's another of the dimensions? What do you think, Al? Top minus bottom. That's the base. So I'm going to just put S of X there. It's that. I don't want to rewrite it. What's the third dimension, Felicia? dx from -1 to 2. It's a really hard topic that I'm trying to make really easy. I don't know how I'm doing. How am I doing? It's not memorizing. What if it had said height's twice the base? How would it be different? What do you think, Priestley? If it said the height, oh, here's one. Letter C. You're my first hour with this. Here it is. This time it says height 5 times the base. You go set it up. Should be memorized. Right? 3 dimensions. Let's see how we do. Still, -1 to 2. We're sweeping across that bread loaf pan. We're building it up with rectangles 5 times the base. That would have been really ugly on this one, because this is just twice the base, and it's already flippy floppy, right? 5 times the base would really dome it out. So let's start. Who did I pick on? Mal, what's one of the dimensions? S of X. Yep, that base. Charlie, what's another of the dimensions? Almost. It's not constantly though 5. It's 5 times the base. So tweak it a little bit. Here's your base. We need 5 times the base. Right? A little difference. It wasn't constantly 5. What's my third dimension, Bryce? Here it is. So really, if we were to set this up, we would say 5 and come out front. And then we'd have that S of X squared dx. We cleaned it up. Do you see the difference between height is 2 versus height is 2 times the base? A little bit difference. Now you're nodding, Frankie. All right, we don't do quarter circles because it's not on the AP exam. Kaden probably remembers the multiplier out front. They almost all have a side squared in them, except that rectangle where it's constantly 2. That's the square. Half of that's the isosceles, the leg across the base. What did the semicircle have? Pi, right, over 8. You do need to memorize that. Resume. It's to your benefit too. Isosceles right triangle, where the base is the short leg, like not the hypotenuse. So it's like this. It's almost a square. That's the square, side by side, right, Clocker? What do I put out front when there's a leg across the base? Hold it up. Here's my isosceles triangle with a leg across the Here's my isosceles triangle with a leg across the base. Just putting that S squared gives me the square. What needs to be put in front of it? Nope, that's an equilateral. Let's kind of look at this. What do you think, Harper? It's almost exactly the same. Half. Yes, it's a half of a square. Equilateral triangle, Clocker, that's this one. Rarely will you see it. You probably need to look at it for your homework. But if it pops up, that's the root 3/4. All right, -1 to 2 side squared. It's a very difficult topic. It's almost time to go. So we'll pick it up from here tomorrow. And your homework is delta math. Where you just be setting them up and clicking, kind of like yesterday. It shouldn't be too long. Getting the phone divide today. Is it hard? No, Felicia? What? Not too bad, Charlie? Is it hard? Is that alright? Alright. You guys just tired today? You were a lot more lively yesterday. Lisa, you tired? A little bit. Oh, I'm going to stop this. If I can. It won't deactivate my fingertip.